Okay, any questions about significance testing? Last class, we started talking about significance testing. We talked about t-tests. We talked about the KS test. Um, any questions about these kinds of things? As it turns out, in some project I was working on with graduate student, a student yesterday, we happened to use the KS test to tell the difference between two distributions. And again, we were giving poll data to people. We were giving people polls about what they thought what they felt about AI and whether they trusted it or not. And we had, a couple of breakdowns of different populations, men versus women, people from the Midwest and people from the rest of the country. And we wanted to see whether or not they had a different feelings towards the degree of trust in AI. And basically, we ended up using a KS test for it. We had a score that we had developed that measured trust from the survey. And we plotted the cumulative distribution of one distribution and the cumulative distribution of another. And based on the gap here, the KS test routine gave us a p-value for how likely these differences were by chance. Any questions on this? Okay, now I seem to have a little problem. Give me 1 second. Okay. What I'd like to spend a little more time today talking about significance testing. And there is a particular problem on significance testing that tends to come up with computer scientists quite often. And it's kind of posed an example of this. There was a very, very interesting book I read of, I'm not remembering what the title is, but this gentleman analyzed a lot of time series data and produced a sequence of amazing graphs showing correlations like this. The one in the corner is showing us, it's a plot as a function of time of the amount of revenue generated by video game arcades and the number of PhD degrees in computer science awarded. And as you notice, there is a tremendous, a tremendous correlation between these two, okay? It is clear that when, it looks like, again, we have to figure out which way the causality goes. But if I look at this thing, it seems to say that when you award more degrees in computer science, it drives people to the video game arcade. Or when people go to the video arcade, it drives them to get PhDs in computer science. Which do we think is the explanation for this beautiful high correlation? Does anybody have an idea of why this is correlated and how significant this should be? Anybody out there? Do people believe that this shows, okay, yes?
I was going to ask, I can't see the chart so well. Is there a p-value given?
Is there a p-value? Well, there is no p-value shown here, but I will say that a correlation as good as this, okay, would have a p-value. So this is an extremely high correlation. This is, would have a p-value that is easily under, let's say, I will say a p-value of, certainly rises to the 0.05 level of significance and possibly higher, okay? The question is, why do we get such a high correlation? Okay, what does it mean? Is it significant to the level of 0.05 of 1 in 20 chance? Oh, almost certainly. Okay, I don't have the number here. That's why I'm saying almost. I'm quite sure that will rise to it. Does anybody see where there's a problem? Or do people believe this? Are people going to go out there, if you're studying for a PhD in computer science, you're going to start playing more video games to keep the significance up? Okay. What is the source of the problem? Does anybody see this? The problem is actually not with the data here or the chart. The problem was with how the data was analyzed. What happened was this guy wrote this book, took a large number of time series, wrote something that compared every pair of time series and looked for pairs that had unbelievably high correlation, okay? And the ones that looked funny enough, he published in this book, okay? So what is the issue here? The issue is that sometimes the data the observation of what of a particular correlation, even if it's very, very high, is not really enough to be significant, okay? Because if you had a 1 in 20 chance of a result this strong coming up by chance, if you do millions and millions of comparisons, you're going to get 1/20th of them showing things as strong as this, okay? And so we need to have some kind of a correction, okay, that will find a way to punish people for doing, if they discover their observation in the course of a search for millions of observations. For something to be really impressive, it has to rise to a higher level. Okay? Any questions about this? Computer scientists tend to fall victim to this kind of thing because we like to write programs. And we're very, very happy to take all pairs of your features and do some kind of correlation over time, or a correlation over a pair of people with those two features. Okay? So there is a statistical correction called the Bonferroni correction, which is very important, which is which is that basically if you're testing n different hypotheses, for us to be impressed, okay, at a level, significance level of, this is the significance level, we call that alpha, okay? If you're testing n hypotheses to be impressed, okay, basically we have to have, the hypothesis has to be, not occur by chance with a, no, excuse me, this is alpha over n, excuse me. At a level of alpha over n. So if you get something that you want to prove that the chance of this happening by chance, the observation happening by chance was 1 out of 20, and you're testing 1,000,000 hypotheses, the hypothesis that you want to trust with that had better rise to a level of 0.05 over 1,000,000. Okay? Any questions about this? So when you're doing multiple hypothesis testing, the Bonferroni correction is an important thing. Okay? Any questions? This is the source of all kinds of statistical sins when people do these kinds of tests. There is a guy, there is, if you Google butter production in Bangladesh, okay, there is a guy who once tried to predict the stock market, okay, based on what was the, he got a big data set of time series from the United Nations, and he tried to figure out which time series would correlate best with what the stock market would do that year. So that way you would know, if you could look at this number, you could predict whether stocks would go up or not. And it turned out that on all these things, the thing that predicted the US stock market the best was the amount of butter that was produced in Bangladesh. Okay. Was there a causal relationship? Okay. And the answer was no. There was a spurious relationship because he, tried millions of time series, and this is the one that happened to do best. Any questions? Okay. All kinds of interesting spurious correlations can exist. There was a time when the winner of the Super Bowl would predict, America's football Super Bowl would predict whether the stock market would go up. And basically that was very impressive up until the moment people noticed it. And then because it was purely a spurious thing, it fell back. Any questions about the Bonferroni correction?
Professor, shouldn't it be n by alpha instead of alpha by n?
Okay, I didn't quite hear that. Does anybody, try it again, speak more clearly into the mic.
Uh, you have written in the slide, in testing n hypotheses, one must to a level of alpha by n. I'm saying that it should be n by alpha probably.
N by alpha, okay? So the answer is we would like, what do we want? The probability of it happening by chance, okay? The more, we want to have a stricter standard, okay, of of evidence for a hypothesis when we are running a lot of these things. So what happened if, let's say I was testing 10 hypotheses and I wanted to have some result that I believed with a probability of 1 out of 20? Well, if I divide this by 10, this comes out to be 0.005, right? And this would be 5 out of 1,000 instead of 5 out of 100, okay? So no, I'm right, that basically that when you test more and more hypotheses, for me to be impressed with one of them, it has to be significant to a higher level, okay? The probability of it happening by, the observation happening by chance has to be a lot lower than what I would have accepted before. If you're only making one theory and you're trying it and you're right to a level of 1 out of 20, I think you got something, okay? If you're trying 10 theories, you'd better have something that comes out at a level of 5 out of 1,000 for me to be as impressed with the truth of that theory. Does that answer your question?
Yeah, yes, thank you.
Okay, any other questions about the Bonferroni correction?
I have a question.
Yes.
Like for example, if n is very large, like millions of hypotheses, so the scaled alpha should be very, very tiny, very little. So there nothing can be detected if the scaled alpha is so small. So so is there any way to
Not nothing can be detected, but you'd better have a really, really strong effect if I'm going to be impressed by it. Okay? That's what kind of I'm saying here. Certainly there are, there are things that the odds of it happening by chance is, 1 out of 10 to the, 10 to the 10th, 1 out of 10 to the 100th, okay? So there are things that hypotheses where the significance level, the likelihood it came by chance, would be very, very low. But you need a really large number, you would need a large number of, here n is the number of hypotheses. Notice that if you were doing an experiment, we usually use n to denote the number of samples, okay? For something to be really significant, you probably need to have a large number of samples and a very big difference between the distributions. And then even if you're testing a large number of hypotheses, then something that stood out that much we would respect, okay? But this is an argument about being very, very careful on doing big fishing expeditions. Any questions? Now, usually when you look at, there's this idea that when you normally make a hypothesis, you make the hypothesis beforehand, and then you do the test, and my God, look, I'm right, okay? It's much less impressive if you are doing many tests, okay? Something comes out, and then you need a stronger set of evidence in order to believe it. That's kind of what we're saying here. Any questions? Okay, this is an important thing. And again, there's other ways of doing it. If you're interested in these things, there's methods for testing, things called false discovery rate. That's another way of doing it. But the idea is important. If you're doing a fishing expedition, for me to believe your hypothesis, you can't just cherry pick the best one. Any questions? Okay, so what is the notion of significance? What is the significance of significance? Statistical significance is what is the likelihood we would have seen this effect by chance. And when you have a large enough sample size, very, very small differences can register as highly significant. Okay? What significance does is kind of measure the confidence that there is a difference between two distributions. It doesn't tell you about the importance of the difference. It just tells you that there is a difference, okay? And how much you should believe that there's a difference. The effect size is an idea that captures what is the importance of the difference. So what is a measure of effect size? Okay, well, people, the correlation, okay, remember, is kind of giving you Pearson's correlation coefficient. That kind of gave you the degree to which one variable would enable you to predict the other variable, okay? Assuming you have a large enough n where it's significant, okay? You can, if you have a correlation of above 0.8, that's considered to be a large effect. Again, on your homeworks, we had 2 TAs grading your homeworks, the same homework, and the correlation was 0.86. Was it statistically significant that they were grading and getting, should they have gotten such a high correlation by chance? The answer is very unlikely if they're grading 70 papers. And, okay, it predicts a large amount of the variance. That's a large effect. Correlations as low as 0.2 or even lower can be statistically significant with large enough n. But, the amount of predictability it gets you is very little, okay? So the correlation coefficient is a measure of effect size. The degree of overlap between two distributions. If I have two distributions here, and I want to say, are these distributions the same? Okay, well, kind of when there is a large overlap between the distributions, then probably one distribution predicts the other, that the thing that is driving this distribution is driving that distribution. And again, these are sort of standard boundaries for what people consider to be impressive or unimpressive effects. Same thing with Cohen's d. This was kind of something that if the difference of the mean divided by the standard deviation, okay, if that difference is large enough, I guess it should be like that, then we would call that a large effect. Any questions about it? Do people get the difference between significance and effect size? Any questions? Significance is there, what's the likelihood it happened by chance? Effect size captures more of does it really matter? Okay, and those are two different issues. Any questions? Okay, I would like to describe now one more approach to kind of generating, kind of p-values, generating statistical significance ideas, okay? You know, the statistical tests that statisticians use that I tried to talk about a little bit, like the t-test and the KS test, there are some subtleties to these tests, okay? So you have to kind of know a little bit about what you're doing. There is kind of this assumption resting on, you know, sometimes they say they will only work based on whether one of the distributions is normally distributed. Sometimes they will say, oh, do you mean that you're trying to tell whether there's the difference is big enough? Is it a one-sided test or a two-sided test? There's subtleties that come in. There is another way to try to get confidence in whether some kind of an observation is happening by chance that I think is more appealing in certain ways to computational people, okay? These idea of using permutation tests. And so I'd like to kind of go through that as the last thing that I want to talk about for now in significance. And the basic idea of a permutation test is that if you have a hypothesis, you say my data shows that people A are smarter than people B, okay? How would you convince me of that, okay? Well, you should be able to, if there's some predictive power, okay, to the difference you see between these two populations, then if you randomly shuffle the data, okay, you shouldn't see the same thing, okay? And that, you know, of course, if you randomly shuffle data, maybe by chance, it'll show an even stronger effect. Sometimes it will do it if you shuffle it enough times. But generally speaking, you kind of know something about how random shuffle data should look like. And a permutation test, okay, is a way of giving you a p-value, a likelihood that something happened by chance. And it does it by generating you start out with some kind of a statistic that you think is interesting. You're looking at your data, maybe the correlation between variable X and Y, okay? Maybe the error of a model, okay? That if you try to predict something based on something else, you get a certain level of error and that's the small error you think is interesting, okay? A permutation test gives you a way to tell whether or not something like that would happen by chance. So what is the idea here? And again, for the homework, you have to do a permutation test. So I want you to try to tell this thing. On the left, we have a, a data set where we have a certain number of women, a certain number of men, and we have the height of these people. So for each one of these bars represents the height of somebody, okay? I think that that's right, okay, in this example. Let's take a look at it. And based on this thing, it might be reasonable to look at this and say, the average man is tall, men are taller than women on average, okay? That might be a, the observation you get, but it's a little bit subtle. This woman over here is taller than all but those men. Does everybody kind of see that? So it's certainly not true that all men are bigger than all women. How would we like to know whether or not there was a difference between the heights of men and women? Okay. Well, one idea that we could do is to take all the heights and randomly shuffle them. Each row here corresponds to a particular person, okay? And we now take we now randomly shuffle the heights of all the people, okay? And put them in some order. Some of these heights are going to be connected with women. Some of them are going to be connected with men. We create an artificial data set of heights, okay? By randomly permuting the heights and assigning them to men and women. When we do that, if we now sort these, as you'll notice, we have, these are our fake women and their heights, and the fake men and their heights. If we had some kind of a statistic that would measure the difference between, so we might want to take a look and say, one statistic might be the average height of the men minus the average height of the women. Okay? That would be a statistic S. Okay? And for this one, it's clear to me that the average male height would be a little bit bigger. It would be somewhat bigger than the average female height. Here, we've got our fake men and our fake women. We can compute the average height of the fake men and the average height of the fake women and compute the difference. And generally speaking, okay, if there is a significant difference between the height of real men and real women, we will tell, because in a bunch of these sample permutations, the difference we observe in the real data is bigger than the difference we observe in the fake data. Okay? Any questions?
Yeah, I have a question.
Yes.
So if we shuffle the data, can we expect the means to be about the same for the two groups?
Yes, we would expect that the means would be about the same. Okay, that's what I would kind of expect. And the question now is, how unusual is it that I see a difference? Well, first of all, would we expect the means to be the same? Exactly the same.
Well, no, very nearly.
You say very nearly. Now, what is the statistical significance test? Are men and women's heights nearly the same? Depends what you mean by nearly, okay? You know, men are not a mile tall and women 6 inches tall. There's a difference on average. There's a small difference we observe. If we want to figure out how interesting a difference it is, okay, let's compare it to the variation we would get by just randomly sampling. That's kind of the idea of the permutation test. Okay? Is that clear?
Yes.
Okay, so what would we expect? Let's just try to look at it. We agree that if we randomly sampled things, sometimes the fake men would be taller than the fake women. Sometimes the fake women would be taller than the fake men. It's probably going to be something normally like the curve, where it's centered around, the difference centered around 0. Now, if we look at the difference of this, where we have done a large number of permutations, okay, we then compare the distribution we get with with what the observed difference was between the men and the women. If the observed difference lay over here in the middle of the distribution, I'm not very impressed. It was presumably something that could be easily explained by chance. Okay? If, on the other hand, I have a world where the real observation lies pretty far from most of the probability, then this is something that probably could not have been happening by chance. Okay? And depending upon how many, if I do a lot of samples, a few of them might rise above better than chance. The probability I would have gotten an observation like this, okay, by chance, would be basically the size of that probability mass, okay? And basically the fraction of things that occurred by chance bigger than me, okay? This will give me a p-value of how unlikely is it that big a difference of height between the real men and the real women was something that was observed by chance. Any questions about that? People see how this kind of thing works? You create a statistic, okay? You then do a random sampling of these things, Okay, you see where the real number ranks among the random samples, and the degree of extremity there is what gives you your p-value. Any questions? So typically to do this, we want to try a large number of random permutations, perhaps one out of perhaps 1,000, perhaps 1,000,000. Probably it depends upon how expensive it is to do this experiment. Okay. And again, the interest that we're concerned with, the more experiments we do, the finer an estimate we get of how much of the tail is to the right of the observation. And that gives us a more accurate bound as to how unusual this thing was. The other thing is that there's a certain level of care that needs to be done when you do the permutation to make sure that you're doing, keeping things kind of consistent, okay? Typically, the thing to permute is the label that you're kind of trying to test. If let's say that I have a world where I've got, n people, I've got 3 features, and I've got a label, okay, of maybe being men or women, something like that. Permuting the, the label and keeping the records consistent makes sense to me. Permuting all 3 of these fields randomly does not make sense to me, because there is typically something, there may be a correlation between 2 of the features, okay? Let's say you're trying to build a model, you have a model to predict, is somebody a man or a woman from 3 different fields, okay? To test how good your model is, okay, whether it's doing it by chance, okay? I'd rather permute the label than permute the individual feature values, because then I'm going to create fake people with combinations of feature values that may not make sense, okay? And so, typically you want to compute what I'll say is the labels, okay? Or you may want to permute the time points within a record, okay? You have to be a little honest when you're doing these kind of permutation tests, okay? And if you do a permutation test and you now train models on the permuted data and they're doing very well, that is often a sign of a problem in something that you're doing, okay? Because typically if you're building models based on permuted data, you would like it to be the case that there was no ability to predict anything. If you are able to predict it from the permuted data, then you've probably got a problem. Any questions?
How do we compare one permutation to another? I was just confused on like how we tell how good one was.
You don't compare one permutation to each other. You're comparing the scores to each other. So the permutation, let's get back here. Where was the permutation in this? The permutation was in scrambling the heights, okay, associated with the individual people, right? Each permutation gave you a scramble. You then computed a statistic, okay, on what was the difference between the male heights and female heights for this new scrambled data, okay? And what we're interested in is how did the real value score against the distribution of results from these random permutations? Does that answer your question?
A little bit. So we're looking for the probability that we get a permutation that's greater than that?
That's basically right. What's the probability? What we're really doing is saying is, what is the probability that randomly scrambled data gave us as impressive a result?
So question, how do you do that without just like randomly scrambling like 1 billion times and then finding a statistic that's bigger than that?
Well, okay, how do you do it except scrambling at 1 billion? Well, 1 billion is a large number. If there is a strong enough effect you should be able to see it with far fewer than 1 billion scrambles. Okay? Let's say you're trying to convince me that there is a 1 in 20 chance that this happened by chance. Less than 1 in 20 chance by happening by chance. If you show me 100 permutations, do you think that you would be able to get a sense as to whether, 5 of them happened, you saw more than 5 examples that were better than random examples that were better than what you saw? So the more permutations to run, the more confident you get in your p-value, the more extreme a p-value you can actually get. But but you don't need to do 1 billion of them. Any questions? Does that answer your question?
I think so.
Okay, good man. So recognize that what a permutation test really gives you is what is the probability of your data given the hypothesis, okay? Once you have decided that men are likely to be taller on women, you're kind of getting the sense of what is the chance that you're going to be, you got data like this, data this unbalanced by men and women, by chance, okay? This isn't quite the same thing as what is the probability of your hypothesis given your data, okay? This is what statistical testing is likely to do, tries to do. Now, by Bayes' theorem, we kind of are used to the idea that we can flip conditional probabilities and that one is correlated with the other, okay? But there are other, there are other parameters in Bayes' theorem other than just this one term, okay? So, there are, there is a subtle difference here, but I still think that a permutation test is a good way to give you some confidence in whether something is happening by chance. Okay? Any questions? It's a good way of keeping you honest on some level. So how do we construct random permutations? Okay? One thing I want to convince you now is that constructing things at random, where things are really uniformly at random, is a very subtle problem. Here I give you 2 different algorithms for constructing random permutations. What am I doing? I'm starting out at the beginning, putting it with an array and putting n numbers in it. Then I am doing n random swaps, where I am taking the ith element and swapping it at random with another element. Does anybody see what the difference between these 2 algorithms is? Is there any difference between these 2 algorithms? Or are they the exact same piece of code? Are these 2 the same piece of code, or is there a difference here?
I think I like the top one more.
But what's the difference? What is the difference?
It's where it's choosing the swaps from.
Okay, this is the difference, just in case you can't see it. It's a question of where are you picking the swap from? With the first one, you are picking the swap from, from basically the swap, you're swapping the ith element in the array with an element from, basically I to n. And the other one, you're swapping the ith element in the array with any one of the other elements. Which one of these is going to generate random permutations uniformly? Or is there going to be a bias? And how can you tell? Who here likes the first one? Anyone liking the first one? Heard one person like the first one. Anyone like the second? What?
I think the second one is better.
You think the second one is better? Why is the second one better?
In the first one, the elements towards the last element, I mean, the elements which are towards the last part of the array will remain clustered over there.
You're saying that the elements in the last part of the element may move more times. Okay? That by the end of the thing, we're almost certainly going to swap with one of those, and that bothers you. Okay? Is there anybody who likes the first one better? Okay? I like the first one better. Why do I like the first one better? Well, my argument is the first one is going to be right because what's going to happen on the first one? I'm going to swap the first element with a random one. It could have been any one. So I know that the first element is uniformly likely to be any of the other items. And then I'm never going to touch it again. Okay? And the same argument I'm going to repeat with all the others. Okay? So I believe the first one is better. Let's take a plot and see this. Okay? Here, I use these two random generation algorithms to construct a million different random permutations of 4 items. There's 24 of them. Okay? Note that the frequencies I observe in blue on the truly random algorithm were very, very consistent across certain permutations, across all the permutations. The second algorithm, where I where I pick at every time I do n swaps and swap over the entire range all the time. Certain permutations occur, in this case, 8 times more often than certain other ones. It seems that the algorithm seems to favor having permutations that start with small numbers, punish the ones that start with high numbers. Okay? It should be clear from this observation that there is a difference between the two algorithms. And one of them generated the permutations uniformly, and one of them had a bias, possibly a subtle bias. If you did a permutation test where there was a bias, would you get meaningful results? No, okay, because you'd be getting, if in fact it was sampling things so the men stayed all together, but were more likely to stay together, then you would probably under-recognize whether the difference between height between men and women was interesting. Okay, so understand that random sampling algorithms are very subtle things. Okay, and that when you're doing random sampling, which is a common thing to do in simulations and statistics and a lot of things, you've got to be careful with that. Any questions of how you generate a random permutation and why there is a difference?
Professor, can you again go why you think that in the first algorithm it's working better for creating
Okay,
random?
so why do I believe it? Okay, my proof is sort of going to be, first of all, is the probability of getting every element in the first position equally likely? Okay, I'm going to say the answer is yes on this one. Why? Because what is this thing doing? The first swap is going to swap the first element with any one of the n elements. Okay? Clearly, any one of the n elements is equally likely to end up in that first position after the swap, and we're never going to touch it again. Okay? So this is why I believe the first element is uniformly distributed, and the second element is going to be by the same argument, uniformly distributed among anything that wasn't the first element, ... That is my argument for why this is correct. What is the likelihood of what ends up in the first position? Well, after the first swap, it's equally likely to be any one of the other elements. but there is a non-trivial chance that one of the other elements is going to get bombed and swapped into there. Okay? And maybe it's going to be the ones that are in the last positions are maybe more likely to get there. I don't know quite what's happening, but I don't know how to think about that. So I know how to think about this. I don't know how to think about this. And when I do my experiment, it's clear that that the one I give you, which is called, I think, the Fisher-Yates method, okay, gives you uniform permutations where the other one does not. Any questions? So again, this is the argument that basically I give you, okay? And the key moral here is that when you're doing random sampling, okay, random permutations and random sampling, this is often a very subtle problem. And one good thing to do whenever you do any random sampling is to tell whether your procedure is really random, is to do a significance test. What is the likelihood that what you observe, the distribution you observe after you do your random sampling, was generated by a truly random thing, okay, process, okay, a uniform selection process, okay? So whenever I do a random generation, because I know that it's easy to get that wrong, I will do a statistical significance test. Any questions? What's a way to draw sample points uniformly from a circle? Let's say I wanted to do sampling of points from a circle. Can anybody give me a random generation algorithm to generate points from a circle uniformly? Typically, you've got a random number generator that you can trust to generate numbers uniformly in an interval, typically from 0 to 1. How would we generate points uniformly in the circle?
Could we use polar coordinates and then do one for angle and then one for distance
Okay, so
from center?
your idea for polar coordinates is you'll say, well, any point here is defined by a distance from the radius and an angle. Is that right?
Yeah,
That's I think what we mean by polar coordinates. Is that right?
Yep.
So one possibility is we sample the angle but uniformly between 0 and 2 pi, okay? And we sample the radius uniformly between 0 and r. And in polar coordinates, we get a point. I agree that that's going to give us samples, that every point's going to lie in a circle. The question is that uniformly distributed? Which of these two is uniformly distributed? Which do you think is more a uniform sampling? Is it the one on the left or the one on the right?
One on the left.
One on the left, that's obvious. Is polar sampling going to give us uniformly distributed points?
I think polar coordinates will not give a uniformly random distributed
What's the problem
points.
with polar coordinates?
Something to do with points towards the boundary have similar angles.
Points towards the boundary have similar angle? That doesn't bother me. If you sample with a high enough, your real numbers are, you're trying to say I can't tell the difference between this point and this point because the angle is too small. This doesn't trouble me, okay? But there is something about polar coordinates that does trouble me, however. What fraction of the points are going to be in a radius from 0 to 0.5, right? If we think about it, the radius goes between 0 and 1. What fraction of the time when we did the polar thing, does everybody think, what fraction of the time will the sampled radius be between 0 and 0.5 as opposed, of all the times that we did the sampling? let me go back and say that again, since that may have been confusing.
Yeah.
If I'm sampling the radius between 0 and 1, and it's a uniform random number between 0 and 1, half the time the radius is going to be less than a half. Does everybody agree with that?
Yes.
But is half the circle, area of the circle, the inner half circle here? Does everybody see that this thing is a circle of radius 1/2? Okay? Is that half the area of the circle?
No, because you calculate the area of radius squared.
Yeah, so the answer is no. More of the area of the circle lies outside that radius. And so if we did sampling, what would end up happening is, if you use the polar coordinates, a lot more of all the points lie within the center, the middle, the inner half of the circle, than lie on the outer half of the circle. So this came from polar coordinates. Okay? Does everybody see how that is going to not generate uniform samples? Any questions? Random sampling problems are more subtle than they look. Okay? Any question? And that's basically the reasoning that I did. How, on the other hand, can I generate uniform random samples? What if I sample X and Y coordinates uniformly within the box containing the circle, and then discard those that are outside the box? How did I generate this nice uniform thing? I put a box around the circle. If my radius was 1, I put a box that went from 1 to -1, -1 to 1, okay? And I randomly sampled points all within this box, okay? And any point that was outside the shape, okay, I discarded, okay? And I only kept the samples that lie within the box. Any questions about that? Does everybody see now I'm sampling uniformly within the circle? Okay? Any questions about that? Do people see how I did that with that Monte Carlo generation? Any questions or comments? Okay. So this is a way to, to generally do random sampling in a correct way, a simple and correct way, is to basically come up with a bounding box of your region and just take the samples that lie within it. Can anybody think of a limitation of that method? Is there a time when that method would be inefficient?
It's wasteful for objects that are basically like a diagonal line, like a really diagonal rectangle.
Yeah, now what if, let's say, I wanted to sample from a very, very skinny X, let's just say, that's sort of your slight your diagonal line is fine, by the way. But what if I wanted to sample by this? You're saying, well, put a bounding box on it. Okay? And now when I sample, almost all of my samples will be outside the box. And so this would be inefficient. Okay? The samples I get would be correct. It would be uniformly distributed within that weird shape. Okay? But this would be inefficient. Any questions about it?
Professor, I think there is a subtle bias here too, that let's just say that when you drew the bounding box, the row at the middle will always get points that are never going to be discarded, but the row at the top will get a lot of points that will get discarded. So there will be a bias towards the central position of the.
You say that there is not going to be a bias. What I'm going to see at the end after I've thrown it out is going to look very uniform. what you're saying is it was harder work to get samples in the center than it was to get samples on this row up here. But that doesn't matter. Once we've thrown out the ones that are outside the box, what's left is uniformly sampled, uniformly distributed. Okay? So there
Right, yeah.
isn't a bias. Okay? You agree?
Yeah, I agree. I actually misunderstood one part. So yeah.
Okay, good. Okay.
I have a question.
Yes.
Could you sort of adjust for that extra work thing by doing smaller squares around sections of the X, or is that?
So you're trying to say, oh, could I adjust by doing certain sampling things and making sure I don't sample? Recognize that what was beautiful about this Monte Carlo sampling technique that I was talking about was that it was felony dumb, that it was very, very simple. Again, is it clear that we can generate a point independent in a box? Yes, then because the two coordinates are independent in a box, okay, for points in a box. When you start trying to get clever, you always have the opportunity to make mistakes, okay? So again, the guy with polar coordinates was trying to get clever, okay? So my instinct here is you've got to guard against. Are there ways that you might be able to do it more efficiently than what I'm talking about, depending upon the nature of your shape? The answer probably is yes, okay? But recognize that it comes at a risk that, there is subtlety here. And it's very easy for you to think you're smarter than you really are. Any questions?
Okay, thank you. That makes sense.
Okay, fair enough. There's one final sort of sampling thing I think I want to talk about. Maybe let's just think about it. One was the question of how do you sample from any probability distribution? I think everybody here knows that they can call a random number generator, okay, and sample things from a uniform distribution. Okay, I think maybe this is what I really wanted to see. If I had a uniform distribution, okay, where I was sampling, the probability of any value from 1 to n was 1 out of n. I think everybody believes that you can do that with a random number generator. Okay, there's classic random number generators like the linear congruential generators and things like that generate that. And you know that there's that API in any programming language. There's a library function for that. How would you sample randomly from an arbitrary probability distribution? Here, for example, is the normal distribution. If I wanted to generate samples from the normal distribution, how might I do that? Okay, does everybody see here I've got X? This is the probability of having X. Suppose I told you that my probability density function was a normal function. How could I randomly sample normally distributed numbers? Okay. The easiest technique is to take your probability density function and convert it to a, a cumulative distribution function. That's the thing on the right. Now notice that basically the entire probability mass is here, and the y-axis goes from 0 to 1. Suppose you sample a number, a probability, get a random number from 0 to 1. That's easy to do uniformly. Now, if we want to get a normally distributed value, suppose we now look and see what is the X that gave me that random number as the Y in the cumulative distribution function. If so, that is going to be my random sample. If I take another random sample, I get another number between 0 and 1. I walk across and hit the thing and go down. Does everybody see that in this case, okay, when I do this sampling, I'm going to get a lot of the values are going to lie in this narrow value of X, because within that value of X is where most of the probability mass lies. Okay? So for any distribution in one dimension, okay, my claim would be this gives you a way of sampling values from that probability distribution. Any questions about that? Does this kind of make sense? Okay, so this is sometimes a very useful thing to be able to do. Any questions about how we do random sampling? Okay, and once you can do random sampling, there's all kinds of, and you can do these kind of, you can start to do samples, simulations or draw random samples. You can start to learn how weird something is, okay? Now, hopefully at the beginning of the semester, I turned all of you into baseball fans. There is a very famous record in baseball, okay, of what is the most number of games in a row that somebody got a hit in, okay? And and a guy named Joe DiMaggio hit 56 straight games, got hits in 56 straight games, and this is one of the famous unusual records in baseball. Now the question is, how unusual should it have been that he was able to, at some point in his career, get hits in 56 straight games? If you look at his record, he got hits in roughly 80% of the games that he played. What is the likelihood he could have gone 56 straight, assuming he played for a certain number of years? What is the likelihood he should have been able to have a stretch where he played 56 straight games without missing? Okay. Well, that is kind of a Poisson distribution if you think about it a little bit, right? Because it was kind of like 80% of the time he was going to get a hit, 20% of the time he was going to die. What's the probability that he would go 56 games before dying? But the way that when I wanted to find out how unusual is this, is I used random numbers to simulate careers and got what was the likelihood that I observed in fake DiMaggio careers, a hitting streak as long as 56. And again, it was incredibly unusual. If you had somebody who was as great a hitter as he was, okay, and you simulated 100,000 careers for him, only in about 1 out of every 2,000 would there be an interval where he would get 56 or more hits in a row, okay? That's why this is kind of one of the most famous records, because it's really so far out of what could have been expected of someone, even if he was a great hitter, that this is something people think will never be beaten. Any questions? Any questions about random sampling? Okay, p-values, why this is a good thing?
Yeah, actually, I have a question.
Yes.
Going back to the PDF and CDF for random sampling.
Okay.
I kind of didn't really understand how you use the CDF to get the random sampling.
Okay, so what we've got here is, what is the PDF tells you what? It tells you what is the probability of seeing a particular value of X. Okay? What is the CDF telling you? The CDF is telling you what's the probability of getting an X less than, less than something. That's what the cumulative distribution is doing, right?
Yes.
So what does that mean? I'm going to now do a sample. We know that that is going to go from 0 to 1. It is covering the 0 to 1 covers the entire probability mass. Now what am I going to do? I'm going to randomly sample a number from 0 to 1 uniformly. And when I sample it uniformly, what's going to happen? I get a number from 0 to 1. I am now going to figure out what is the X naught that probability covers. It should be clear for every probability. I am going to be mapping it to a value of X. Okay? And I'm more likely to get values of X which occur frequently, because those are going to be the represent intervals on the line from 0 to 1, okay, that are bigger intervals. Okay, so what am I doing? I'm randomly sampling the Y's uniformly. This is easy to do. And then I'm going to map from that Y value to figure out what X it was that generated it. And these X's are the random samples from the normal distribution.
Okay. Is it a fair intuition to say that the more horizontal parts of the CDF are where you'll get more of your X samples?
That's exactly right. The steeper place of the place where the cumulative distribution is steep is where there is a lot of probability, where you have very frequent values, right? And those are the ones that you're more likely to sample from. That's kind of exactly what the intuition is here, right? Where the CDF is steeper corresponds to high probability items, and those that gives me a fatter X range to hit those values. And that is exactly the intuition of what we're trying to do here.
Okay, great, thank you.
Any questions? Any questions about random sampling or anything like that? Okay, what I'd like to do now for the next thing we're going to talk about, starting next class, we're going to start to talk about visualization. And I think that data visualization is one of the very important things about what you call it. Hold on a second. No, hold on. Okay. Data visualization is one of the very important skills in understanding data sets. And people, it takes practice for people to learn the difference between good and bad visualizations. And that's why I'm going to have this unit, which is going to run a couple of lectures starting next class. But I wanted just to get you guys thinking about it by looking at some of the visualizations that you, the class, submitted for homework 2. And I want us to judge whether things are good plots or bad plots based on what you see. So here is a plot where it looks like the x-axis is when there is a change in price, and the y-axis looks like the number of sales. Okay, what does this plot say? Can anybody read this plot? It looks like every dot represents a product. And what they're trying to show you is what happens when you raise the price to the sales, and what happens when you lower the price to the sales. Does everybody kind of see it? And when I look at this thing, as the prices go up, the more sales are in this quadrant, meaning the sales went down. When the price went down, more products are in this quadrant, meaning the sales went up. Okay? And it's clear that there's relatively few products that raising the price caused more sales or lowering the price caused less sales. Who here thinks this is a good plot? Who here thinks it's a bad plot? Any questions? Do we have good plots or bad plots? Okay. I think this is a very good plot. I think this tells me a story and I understand it. I now see that demand is sensitive to price, right? So I think this is a great plot. We can quibble about whether you like the blue dots or green dots, but I understand it. What about this? Who here likes this plot, thinks this is a good plot? Who here thinks it's a bad plot? Any comments? What does the color tell you? Can anyone tell me what the color tells me?
I have no idea.
You have no idea? I know what the color tells me. It looks like the color is a rainbow. It tells me that X goes from here to this, right? The color shows me where there is a large X or a little x. But how do I know the difference between a large X and a little x? Well, it should be pretty clear that this is a large X and this is a little x, right? I don't need the color. Does the color tell me anything? Okay. I don't think I'm learning very much about the color. Okay, I'm not learning much about the day range. Okay, so I don't think this is a very good plot. And if anyone wants to argue with me, I'm happy to have arguments here. Any questions?
I see at the bottom that they got the labels for probably every single day. What's usually an appropriate bucketing strategy in that case?
Well, okay, so the one thing you're telling me is they proudly displayed the actual date here, but it was too close together. What's clear is you should not have given the label for every single day because it stepped on each other. What is the right sampling strategy? You probably want to have every X date, okay, where X is far enough apart. Maybe you will probably also want dates that mean something. We're used to thinking about, if you showed me the label for every 33rd day, it probably wouldn't mean much to me. If you showed me a label for every week or month or year, then I think I would understand that better. My main beef with this one is the coloring. I can't possibly understand anything. What about this? Do people like this plot? This plot looks like you're showing me the sales for a particular item and the number of sales and the effect of the price on this item. Do people like this plot or not like this plot? Any art critics I've got here? What do people think of this plot?
Is the orange one using a different X scale?
They're using the same X scale, which is year, okay, date, and here they have it according to month. They're using a different Y scale, so they somehow normalize these things. So both of them could appear on the same value. Okay, that could be interesting. Do I learn anything from this? Well, I learned that somehow there's a period of time in Russia where these items get spiked. And sure enough, that looks like Christmas is a good thing, right? And it looks like I see a time when suddenly this item became less popular. So I am able to learn some things from this. Is there any improvement anyone would like to give about this plot? I think this isn't bad. I think this is pretty good. Is there anything that would make this more informative? I am itching to know what item 23,049 is. Do any of you know what item 20,043.9 is? I don't, but I think it would be better if it would make the plot much more interesting if I did, right? But generally, I think that's a pretty good plot. What about this? Some other students submitted this one. Do people like this plot or don't like this plot? It's every bit as blue and orange as the previous plot. What are people's reaction? Not getting much reaction, but I think that people probably don't like this plot
It's
so much.
very confusing because I see like diagonals in places that are weird.
I don't know what I'm seeing here, right? I don't really know, first of all, what the X and the Y is for both of these things. And I don't know what, there's so much line stuff here. It's obscuring any trends I might possibly see. This should be clear as a plot that I don't think can provide any information to anybody, okay? But again, people come up with these things. What about this plot? Is this a good plot or a bad plot? What are people's reaction to this one? I think this is a good plot. I understand what this is telling me. It seems to tell me that there's a bunch of different stores, and this tells me how much stores did they have, how much money did each store make, okay? And I'm getting a sense of what the differences are between these stores. When there is a period, I can see what's going on. This to me is informative, okay? I know what the two biggest, it looks like the biggest stores are generally in Moscow. Maybe this blue one is a little bit lower. That's kind of interesting, okay? Does everybody see how the plot tells a story? This to me is something I like in a plot. What about this one? One of the students submitted this as their plot. Who here likes this one or finds this one interesting? What sins did
Probably
this,
using normalization,
what?
log scales.
Well, there are a lot of different sins on this plot. First of all, it doesn't tell me what the x-axis is or the y-axis or what they're trying to show. So some labels seem like an important thing. But the biggest thing here is that I'm guessing this is something about a frequency as a function of x. It's clear that there's almost no values of x for this, okay? It's clear that the range is wrong, okay? Maybe if you plotted x on a log scale, or maybe if you deleted a small number of outliers and just showed me this range blown up, okay? There would be more buckets here, and that big mass would not all appear in one bucket, but spread out, okay? This tells me nothing, but there's ways of seeing the data that would probably tell me something. Any questions? Here was a plot somebody produced. Looks like they're looking at a bunch of products, and they're trying to see that for some of them, the sales was relatively stable, and for some of them, they fell off the chart. Do people like this one? This
No,
one
there
does
are
look
some
like it's
overlap.
using a log scale, okay? Do people like it or dislike it? Any comments? I like it. I think I'm learning something. What could be done to make me learn more? Any ideas on how this might have been better?
The names could be translated.
I think that unless you're trying to educate someone who's Russian, okay, I'm itching to know what these categories are, okay? And without the label there, okay, putting the label in some other language isn't going to help me. So might as well not put it there. Or better would be to put it in English. Any questions? What about this one? Do people like this plot? Okay. It looks like it's some kind of cumulative distribution based on all kinds of different categories. What do I learn from this? Well, I learned that the cumulative distribution goes up, okay, as you move to the right. But that's true of every cumulative distribution, right? I can't see the products. I don't know if there's an ordering scheme, okay? It's clear that this tells me nothing, okay? Any questions about that? This has at least a labeling sin, okay? Okay, but maybe other things. Any questions? Here is a plot. Do people like this one? This one shows a bunch of cities, okay? And it looks like what's the amount of items sold in each city? Does this tell me a story? This tells me that Moscow is obviously a place that buys a lot more goods than any of these other cities. All these other cities are peanuts. They're about the same size, okay? But the presence in Moscow is wildly greater, and I see both a world where they have growing they have sales peaking around Christmas, as well as a kind of negative trend that isn't good. It looks like these guys are selling less over time. Maybe that's why they went out of business and gave you their data set. Any questions? Any ways we could have improved this? I have probably a minor quibble that I would have wanted to know what month it was, not just the ith month. Okay? To confirm my theory that this is Christmas. Okay? Maybe a better label would have been good. What about this one? Do people like this plot? Does this plot tell you anything? Okay, I don't know what this can help to tell me. Okay?
Not a function.
What? There seems something weird as to why it's going. It looks like it's going backwards. And that leads me to wonder what that connected line means. But it's certainly not obvious from here what this means. Okay, I think the point is made that when given the opportunity to visualize things, some people found meaningful visualizations, some people didn't, okay? The next couple of classes is going to be about trying to learn how you build meaningful visualizations, and that there is a way of thinking about these things that's important. And that's what we're going to start to talk about then. Okay, any questions? Okay, thanks for your attention. I will see you guys next class. And I'm going to go